Welcome back. Today we're going to talk about congruent figures and series of transformations. So the first thing we're going to do is try to perform a series of transformations. So here I have 6 transformations. I'm going to perform them one by one at a time in the order in which they're written, okay? So let me first start by labeling my pre-images vertices, A, B, C. Okay. Now the first thing I want to do is reflect over the x-axis. So to do that, I just count the number of spaces above, and then I mimic that below. So C is 2 above, so C prime is 2 below. B is 2 away from C, so here's 1, 2. This is B prime. Okay. A is 1, 2, 3, 4. So I go 1, 2, 3, 4. This is A prime. Okay. All right, then after that, so I've done this one. Then after that, this says transform by shifting it horizontally, so subtracting 3 from every x coordinate. So that means that we are transforming the figure 3 to the left. And so I'm going to take every point here and travel 1, 2, 3 to the left. So that's A double prime. C is 1, 2, 3 to the left. And B is 1, 2, 3 to the left. Oops. Okay. And then we want to reflect it over the y-axis. So if I do that, A triple prime actually ends up being, since it's on the line of reflection, it actually ends up remaining there. So let me cover it over with a different color. C triple prime ends up being here, and B triple prime ends up being here. Triple prime because it is the third transformation. Okay. So I've done this, then I want to shift it up by 4, okay? So here I want to take every unit, every point and shift it up by 4, so 1, 2, 3, 4. Okay, and C ends up being 2 above 1, 2, 3, 4, and then this is where A 1, 2, 3, 4. So it should have 4 primes on it at this point. Okay, and then I want to rotate it 90 degrees clockwise about the origin. Okay, so 90 degrees clockwise ends up being in this direction. So what essentially is going to happen is, since A triple prime is on the center of rotation, it's going to remain there. So let's again cover it over with a different color here. So this right here is A, and it would be, oh, these are mislabeled, so I'm only at the 5th transformation. So this would also be A 1, 2, 3, 4, 5. Okay, and then B would be 90 degree rotation, so this is -2, 0. So that would jump over to 2, 0, or 0, 2 rather, because the coordinates switch. So this is B 1, 2, 3, 4, 5, and then C, since C is at -2, 3, it would be at C 1, 2, 3, 4, 5 would be at 3, 2. So 1, 2, 3, 1, 2. This is C 1, 2, 3, 4, 5. I know it's really awkward with the primes, but that just denotes that it's the 5th transformation. Okay, so the next thing that I wanted to talk about was comparing the size of the, comparing the size of the final image with the original. So this is asking whether or not these shapes are congruent. Now, we know that reflections, translations, and rotations all maintain congruency. So since all we've done is we've reflected, we've translated, we've reflected, we've translated, we've rotated, what I can say about the pre-image to the final image is that the triangle ABC is congruent to triangle A 1, 2, 3, 4, 5, B 1, 2, 3, 4, 5, and C 1, 2, 3, 4, 5. Okay, I know that they're congruent because the only things that I have been doing is I have been just doing all the transformations that maintain congruency. All right. So this is actually a way to check whether or not it checks the property of each transformation. So you want to take a second and copy this down or print this out for your notes. So a translation, so there's three things that I want to talk about: position, orientation, and size. Right? Position is the vertices of the polygon and whether or not they have different coordinates after the transformation. And translation, reflection, rotation, and dilation, these all change position, except for if the point is on the line of reflection, it doesn't change. The position doesn't change. If the point is in the center of rotation, the position doesn't change. And if the point is on the center of dilation. Now, I know we haven't gone over dilation yet, and we will soon, but this is a handy chart to have, so I've included dilation in this property of transformations chart. Orientation is whether or not the shape looks identical to itself after the transformation. So this is something that's different than position. It's the way that the vertices and the line segments are in relation to each other. So for instance, if I take a triangle here and I just take it and I move it around like this movement doesn't change the orientation of A is always the bottom vertex to the left, C is always the bottom vertex to the right, and so on. So translation does not change orientation. Reflection and rotation does. Reflection changes orientation left, right, or up, down. Rotation rotates the orientation, but dilation will end up not changing the orientation. Okay. And then there's the idea of size, and the only transformation that changes size is the dilation. So for all three of these transformations, translation, reflection, rotation, the figure remains congruent. So that's why this is along all three of these. Translation, reflection, and rotation create congruent figures. Okay, so this actually ends up being very handy in terms of proving that things are congruent to each other. So you can prove that two figures are congruent by finding a sequence of transformations that only include translations, reflections, and rotations that brings one figure to the other figure. So can we prove the figures are congruent? If someone asks me, are the figures below congruent, what I can say is that well, they're congruent if I can find a transformation that includes only these three transformations, meaning I don't have a dilation. So if I can find a series of transformations of these three, then they are congruent. So let's see. The orientation from let's try to find a way to go from figure A to figure B, and let's actually label this D. Okay, E, F, G, H. Let's just do that. So it seems like, so this would be D prime, if this were indeed the pre-image and the image. So we can say that this would be H prime, this would be G prime. So you can tell, let's see, E is over here, this E prime and F prime. The figure has been flipped, the orientation's been flipped left, right. So there's a reflection, because that's how the orientation gets flipped with a reflection. But if I reflect over the x-axis, F prime would show up right here. Okay, so not only has it been reflected, it's actually been translated one to the left. So here's my sequence of transformations. Okay, so the first transformation is that it's been reflected. So x, y goes to, let's see, when you reflect over the y-axis, the x value changes, that x becomes negative and y stays the same. Okay, so you can either write it out with the algebraic properties, or you can just write it out verbal. You can write it out with a description like this: reflection over y-axis. Okay, and then you've translated it. So let me write this down. Translated one left. Okay, so when you've done that, that's the algebraic representation, is that you've taken one away from the x coordinate. Okay, so whatever you arrive at here, this becomes your new xy coordinate, and then you take one away from the x coordinate for all the coordinates, for all the vertices, and then you maintain the y coordinate. So that will allow you to reflect this and then move it. And so actually the figure that I see has been undergone two transformations, so it actually should be double prime. Okay, Let's try it with a different series here, or two different figures. So let's see if we can get from B onto C. Okay, and let me move this over a little bit. All right, so transformation 1, it looks like the orientation has been rotated. So let's see if we can do a 9, if let's label this, I don't know, F. Let's see what F is and see if we can get this to this point right here, because that would be F. I bet it's undergone 2. I'm going to hypothesize it's undergone 2 transformations. So I'm going to call this F double prime for now and change it if I need to change it later. So F is -2, 1, okay? And so if I rotate it 90 degrees, let's see, rotate it would be counterclockwise. Then F prime would go to 1, 2, but then it would be, let's see, this is in the second quadrant, so it would be in the third quadrant, so both of them would be negative. So it would go to -1, 2. This would be F prime. Okay, well that's not where F double prime lands. So here, what I'd have to do after this is I'd have to translate this to the origin, so that would be up 1, and I'm just making a notation and I'll write it more formally in a second. It's up 1 and right 1. Okay, so let's write it in algebraic representation. All right, so xy becomes, let's see, if it's rotated, then it becomes y, comma, and it's rotated counterclockwise, so we take the -y, comma x. So you can see I took the opposite of whatever was in the y coordinate and made it my x, and I kept the x coordinate but just made it my y coordinate. And that's a counterclockwise rotation of 90 degrees. And then translation of up 1, right 1 takes an xy coordinate and it brings it to x plus 1 and y plus 1. Right? I'm adding 1 coordinate for each of them. And then you can always, likewise, you can just write this out verbally. I'm just writing out the algebraic description. You can write it out using words if you need to. But since I found a series of transformations that takes one onto the other, that only involves a rotation and a translation, these two figures are congruent to each other. What I've proven, so therefore, figure B is congruent to figure C. And that's the end of the lesson for today.